Hello and welcome to the seventh lecture to my course on quantum theory and technologies. Last week we talked a lot about the quantum wave function and basically how to define the wave function. And the main point is that wave function is a type of a vector that represents the state of the system. We got on to talking a little bit about one of the features of the wave function, which is that it needs to be a normalized vector. So basically that the length of the vector should be equal to 1. And what I was telling you towards the end there was that this is basically because it's related to the fact that measurements are probabilistic in quantum theory, and probabilities always have to add to 1. So this week, or in this lecture, we're going to talk to you about how measurements actually work in quantum theory. And it'll turn out that measurements are really quite different to what we know from classical physics theory. In fact, you don't really have to even think about measurements so much in regular physics. It's more or less taken for granted that if you have some object, say, it's a ball that's flying in the air, then and it's moving at some velocity, then you can always basically measure that to any arbitrary precision that you like, in principle at least. It turns out that quantum mechanics is a little bit different, and the way that measurements work are actually just a little bit different. And this is why this is one of the strange aspects of quantum theory that, in fact, the thing that you take for granted in classical physics, that if something is somewhere, then you can actually just know where it is and what it's doing. In quantum mechanics, that's actually not necessarily true. So this picture here is just sort of a bit of a schematic for how measurements generally work in quantum theory. Essentially, we always view the some quantum particle, say, going into some kind of measurement device, and then the measurement device tells you something about that particle. And the way that works is what we're going to be talking about in this lecture. So let's sort of recap on where we left off last week. So basically, I was mentioning that sort of vectors need to be normalized, and this is basically because if we actually try and measure these coefficients, then and remember, these coefficients were like we have some wave function, and these a's were actually the coefficients of the actual these states here. So we've got a whole bunch of states here, and the quantum state is written as some vector with these coefficients, these a_n's, right? And we're talking about why this a_n's need to be normalized, or in other words, why this vector here needs to have a length of 1. So it's basically because if we try and measure this quantum state, and we say, okay, so we've got this quantum state. Now I want to know, you know, which state of these n states the state is in. So it's a simple enough question. You've got some state, and you want to figure out, okay, is it in this state or is it in the other state, or there's more than two states. Just try to figure that out. Then basically what happens is that in quantum mechanics, you actually get the result of each of these states completely randomly, and you get it with kind of probability equal to the coefficient absolute value squared. So this, of course, means, going back to our lecture on complex numbers, it's actually an times an star. So that's what's that's what this modulus squared means. It's an times an star. So with that probability, and this is always a real number, by the way. So these an's are complex numbers, but this probability is always real because I don't know how you would interpret complex probabilities. You can't really do that. So with that probability, you get that state n. And so this is a kind of a peculiar aspect of quantum theory, that it's kind of intrinsically random, and there's basically no way around the fact that it's random. So this randomness is not because your system is noisy, or your experiment isn't perfect, or there's some other sources of noise in whatever you're doing. It's really like the fundamental aspect of quantum theory, and it's just an inescapable fact that it's actually random. Okay, so let me just illustrate this with an example here. So here we've got one of the examples that I showed you before. So this is some kind of very small kind of device where you can control some electrons that are going in. Don't worry about all this complicated stuff here. All it basically is you've got some source where electrons can come in, and then they can there's some barrier here, right? And then so it can either go left or it can either go right. And then you got all these little gates here, and that can control or do some stuff to the electron. But the most important fact is that this electron can either go left or it can go right around this barrier. And you can do this in a quantum way, right? So suppose that I have a qubit, and it's in this state that's written like this. So we've got some kind of superposition where 0 is the state where it goes to the left of this barrier here, and 1 is the state that it goes to the right. And say it's traveling through here, it's sort of halfway through its journey, and it's into this. It's basically in this state here, which I've just chosen the numbers fairly randomly, just for the sake of the example. So it's in this particular state, and then now suppose I can use some of these other contacts here, and then try and say, okay, so I want to know, has it gone left or has it gone right? It's a straightforward question. Using my contacts and all this electrical connections, should be able to figure out, has the electron gone left or right? Because you can usually tell if something's gone left or right. For example, like the charge of the electron, you can put some little detector of the charge there, and then you should be able to tell if it's there or not, right? So what happens if you do something like this, and this is like a quantum particle? What happens is that you basically get it with the probabilities according to these numbers here, but the absolute value squared. So we can work out the probability that it goes left, just according to the rules that to the formula that I had on the previous slide. So this should be equal to this coefficient, because 0 is the one that means left, right? So it has to be this coefficient, absolute value squared. Okay, so we can just do that little calculation there. So actually, is a simple way to sort of work this out. If there's any factors of I, you can always forget about it in this absolute value squared, because what happens is that you multiply it by its complex conjugate. Whoops, so this is 2 rather. So this is root 3i over 2 divided by root 3 of minus I. So we've got to change the sign on the I here, right? And then so I times minus I is just 1, because I squared is minus 1. So minus of that is 1. Root 3 times root 3 is 3, and 2 times 2 is 4. So with probability 0.75, you will find that it goes left. And we can just do the same calculation for the one on the right. So the probability has to be basically the modulus squared of this coefficient here. So it's 1 over 2 squared, and there's no complex numbers, so this is just the regular squared. So this is equal to 1/4, or of course equal to 0.25. Okay, so that means that you say we prepare this state, and then 3/4 of the time we'll find it here, and 1/4 of the time we'll find it there, and basically that is your quantum mechanical kind of prediction. So you might ask, okay, so what does that really mean, sort of in the lab? So the thing is that to get probabilities, and this is always true, you actually need to repeat the experiment many, many times. So you can't just do this once, because you send your particle, you've got your state like this, and then say you get, okay, it went left. But that doesn't actually tell you anything about probabilities, because it's like flipping a coin. You get heads, you get, heads once. That doesn't tell you, say, if it's the probability of getting heads was 50-50, as you might expect, or maybe it's like some very biased coin and you always get heads. You need to actually repeat the experiment a lot of times, and then you can work out what the probabilities are. So, so how you would actually do this, so this is actually what people in the lab actually do to figure out these types of probabilities. And I work with experimental groups, and they have some of these advanced quantum computers. Even with these quantum computers, this is exactly what they do. They repeat the same experiment over and over and over and over, and then each time they get a slightly different result, but they keep a tally of all the outcomes that you get. And then finally, then you can work out what the probabilities are. So basically the procedure, and this would be true for a lot of different types of quantum experiments. So what you would do is first you prepare the system in the identical way. So if we're talking about this state, we have some method of preparing that in the same way every single time. Okay, so we prepare that each time. Then we repeat the experiment, say 1,000 times. 1,000 times is a pretty good number. That's quite a large number, so you can get a bit of statistics. Count how many times you get electron in the left channel and the right channel. So okay, so you just count, you repeat it, you get a different outcome each time. Just count how many. So maybe you might get something like 753 times it went left, and then 247 times it went right. And then, so obviously you estimate the probabilities, like you just count the number of times it went left and divide it by the total number. So in this case, you would estimate the probabilities as something like 0.753. Estimate the other probability of it going right as 0.247, and then you compare it to your theoretical answer, and then you go, yeah, okay, that agrees pretty well. It's it's not exactly the same, but we only did this 1,000 times, so we don't expect perfect accuracy, because we didn't repeat it enough times, or in the realistic experiment there's all kinds of other issues. There's actual noise in the experiment and so forth, so nothing ever agrees absolutely perfectly, but within some experimental error you get the expected result. So so that's actually how you actually match up this kind of quantum theory to something in real life, right? So you always match it up using probabilities. There's a couple of things, or well, one thing to notice here is that notice that there's this factor of I here, and basically it didn't really do anything, right? So it you know, if this I wasn't there, actually I still would have got 0.753. Um, in fact, even if this was like a minus sign, say this was minus a half, I'd still also get 0.25. So in terms of this experiment, there are actually, several different types of quantum states that you would actually get exactly the same probabilities as. So you might think, well, all right, then why do you even need these i's or the minus or anything? This seems um, that doesn't really affect things. So the answer to that, which we'll go on to in the next lecture a little bit more, is that actually there's different types of measurements that you can make. This is not the only type of measurement. You can also make measurements in uh, what's called different bases, and then actually these i's and the minus signs, they actually do matter. So there's actually a way of getting information about those. But actually from this type of measurement, it's completely insensitive to the minus sign or the i's. So as far as this particular type of measurement is concerned, actually it doesn't actually make a difference. So actually, even here, where you get this kind of probabilistic outcome, you don't get complete information about the quantum state. So some aspect of the measurement is always a bit hidden when you do some particular measurement, and it's only from actually doing all kinds of different measurements that you actually get the final. You can actually tell what the state actually is. So one measurement doesn't even, or one type of measurement. So this is after repeating it many times. One type of measurement actually only gives you sort of partial information about the quantum state. Okay, but we'll talk about this a little bit more later. Okay, so let's do a sort of a simpler example here. So let's actually just consider a qubit. So this is like a two-level system, and let's also think about what actually happens to the state after you actually measure it. So you might say, okay, so I've started off with my state of a qubit that's in this particular state. Okay, I go and measure it somehow. Now, randomly, I get either 0 or 1, and as I said, the probabilities are according to these factors here. Then you say, okay, so after I've measured it in one of these states, so what is the new state? So is it that state? Is it the state that I started with, or does something happen to it? And so actually, what happens is that after you measure the state, and say you get this outcome of 0, then of course the state is actually in this state 0. So what your experiment is telling you is true. So after you've measured it, it actually changes into this state 0. So there's a kind of a complete change, like what you've done actually by measuring the quantum state is that you've actually also kind of slightly destroyed the actual state. So the measurement actually sort of irreparably modifies the state. And it's irreparably because you cannot really recover the original state from the original state. So after you've done your measurement, you've actually kind of destroyed the state a little bit. Um, uh, so you can maybe get the probabilities of these things, but then you can never really get back the original state. The only way to really get back your original state is just to redo the experiment, and then you re-prepare your state after, using whatever procedure. So measurement in quantum mechanics is actually a kind of a destructive process, and this is a bit different to what we know from classical physics, because, if I just go back to my ball flying through the air example, just because I do some measurement and I say, okay, that ball is in that position and it's flying with that velocity, normally it doesn't change anything about the ball, right? The ball keeps on flying. You take a picture of something, it doesn't really interfere with it. It's just, you're just an observer, which is just looking at the object, and it doesn't really affect the object itself. But actually, in quantum mechanics, the measurement is actually really interfering with the object. So it's kind of it's a destructive process um, that completely changes the nature of the state, right? Okay, so uh, right, so let's talk about then what this notion of this wave function collapse is. So to illustrate this, what we can think about is, so I've done my measurement. I get a particular outcome, 0 or 1 with certain probabilities. And then I say, okay, if I measure it again, what do I get? And of course, I do a quantum mechanical measurement. So say if I make my measure again, then if I'm in this state 0, then in terms of what the coefficients of these states are, remember these alpha and betas are the states that of the coefficients of the states. So, by definition, this is like 1, this is 0, right? Just matching up the coefficients of my arbitrary state here. So 0 plus beta 1, right? So the state is only 0, so beta is 0 and alpha is 1, right? So if we just repeat our procedure for what the probabilities should be, then obviously alpha is 1, so the probability of getting 0 is 1, and the probability of getting 1 is 0, right? So what this says is that after you've measured it, and if you go and measure it again, then you will always just keep on getting that same outcome, right? So this kind of makes sense. It's sort of like saying, you've got your machine here, and then you're saying, okay, I want you to tell me, is it in state 0 or is it in state 1? Okay, and then so you first put in this quantum state, and then this kind of random stuff happens. But after that, after the machine says it is in state 0, then you say you put that back into the machine, then then you say, okay, I know you just told me that it's in state 0. Can you tell me what the state is? And then the machine will go, well, of course, it's in state 0 because I just told you a minute ago that it's in state 0. So it's still in state 0. And so you can repeat that as many times as you want. You can put that again into the machine and say, okay, I know you just told me twice that it's in state 0. Can you tell me what the state is? And then the machine will say, it's still in state 0 because I've already told you 2 times. Right? So this can be repeated as many times, of course, with state 1. And this is basically the notion of this kind of collapse of the wave function. Right? So we started off with this arbitrary state, alpha, beta coefficient, and the measurement, as I said, is some kind of destructive process. It changes the wave function to 0 or 1. And then after that, it basically stays as it is, right? So basically what's happened is that the wave function has kind of collapsed to this 0 or 1, and these are kind of your regular kind of classical states, right? Because this is, for example, going back to our, little channel example, it's the state that it's, definitely in the left channel or it's definitely in the right channel. It's one of those two, right? So uh, if you if you start with this quantum state that's in this superposition, it will, after one measurement, it will collapse to these classical kind of states. And then thereafter, it's just a classical state. It will just be in that state for the whole time. So this is called the collapse of the wave function. And this is one of the sort of the peculiar aspects of quantum theory because again, somehow the measurement is a really a interfering, destructive kind of process, and furthermore, it's kind of random. And actually, how this process really happens is still a little bit of a mystery. So even after 100 years that quantum mechanics has been investigated, how this actually sort of happens, that you start from this quantum state and then you end up in sort of one or the other of the states, is a little bit, this is a kind of a mysterious process, and there's various types of theories, and I think we'll talk about this in another lecture as well, but it's things like the many worlds interpretation of quantum mechanics is kind of talking about this very thing. So, for example, what in the many worlds interpretation of quantum mechanics, some people think that every time you do a measurement, you actually go into sort of a parallel universe where one measurement has happened, and then there's some other parallel universe where you got the other measurement result, and then you kind of keep progressing. This is some way to sort of avoid this kind of discontinuous collapse of the wave function. But personally, I think that those theories are a little bit, kind of out there. I find it kind of hard to believe that there's infinity of universes, and of course, this just gets more and more and more complicated as more and more measurements happen. So it just seems a little bit implausible. I think the people that tend to sort of believe this type of theory is more along the like kind of the purist mathematicians who just look at the equations and say, well, the equations say this, so this is how I interpret the equations. But to me, it's a little bit too far-fetched. So but I think the more conventional way to interpret it is that this kind of discontinuous collapse occurs. We don't really know how or why, this actually happens, but it happens, and that's the fact, right? So this is a so-called Copenhagen type of interpretation. So there are various interpretations. Everybody agrees on what rule that you should be doing. So the rule which I told you is the rule that everybody uses, but how you interpret it has different kinds of there's different interpretations. Okay. Okay. Anyway, we'll probably talk a little bit about that later too. Um, so what I showed you was already the basic way that measurements work. So in a way, that's kind of enough. But another way to actually frame this in a more mathematical theory is the theory of measurement operators. So you can also define measurements and the effect of measurements in this way. So if you if you remember back to our kind of crash course on linear algebra, then operators were basically the kind of tools that you used anytime the vector actually kind of changes. So for example, if you start with one vector and then it changes into some other vector, then you always use like an operator to represent that. So as I've said, the measurement is actually a kind of a destructive, interfering kind of process. It changes the state. So it's natural to use operators to and represent measurements. And it turns out that basically the measurement operators that you want to use are these things called projection operators. So they're called projection operators because essentially what they do, if in a kind of a graphical language, is that say you got like some axes here, and say here's the vector that you start off with. Whoops. Here's the vector that you start off with. So here's my vector psi. Then essentially what these things do is to kind of force this vector onto one of these axes. So it either changes the vector to this vector which is lying parallel to this axis, or it changes this vector to another vector which is parallel to this one. So it kind of takes it from that vector down to this one, or this vector to the vertical one. So projection operators are something that do something like this. So they kind of project the state onto the axes. Okay, but here's basically the general formula for how this works. So there's a measurement operator for each measurement outcome. So for example, say here we were trying to do a measurement of like did the electron go left or right? So there's like kind of two outcomes, and there's a state associated with each outcome here. So there's an operator for each particular outcome. So this is the outcome where it goes left, and this is the outcome where it goes right. So there's a measurement operator each for that. And the way that the operator works is that it's, again, this outer product thing. So if you go back to the linear algebra lecture, then there's the outer product, which creates a kind of a matrix for the state, and this is basically how you construct these operators. So a formula that basically tells you, won't really derive it. In fact, I'm not sure if you even can derive it, because this is sort of like a kind of an axiom of quantum mechanics. Then the probability of obtaining each outcome is given by this expression here. So the way to read this is, so here is our state, and that is a vector, and this measurement operator is some kind of matrix. This is the Emission conjugate matrix. So remember, Emission conjugate means you take the transpose of the matrix, and then you take the complex conjugate, or reverse order is fine. And then here is the conjugate vector. So what this basically looks like is something like this. So the conjugate vector is some vector that's lying down. So here's our conjugate vector state. Here's our measurement operator, and you've got to take the complex conjugate of that. Here's our regular measurement operator, and then here's our state vector like this. So this thing, when you multiply all the matrices, will give you some number, and that number is the probability. The state after the measurement is actually given by this quantity. So it's basically equal to the state after you just multiply the state that you are trying to measure. That's the original state that you're starting with. Here is the measurement operator, and that's basically the new state. But there's a little bit of a kind of a thing that you need to do, which is to get like a normalized state here. You actually need to divide it by this probability here. And if you don't do that, basically it's still almost the right answer, but it's just that it won't be a normalized state. And I've said that any quantum state is always normalized, and if you don't have this factor, then you'll get a vector that's not quite normalized. But it's basically the right answer, actually. Okay. Okay. So now that's probably a little bit, a bit formal. So let's just do an example here. So, suppose we are trying to measure this qubit state here, and we actually already more or less know the answer to this, right? But say we're trying to measure this case, is the qubit in the state 0 or is it the qubit in the state 1? Okay, so we're doing this measurement. So we already know what the answer is, already told you a few slides ago. The probability of getting the state 0 is like absolute value of a, sorry, I should have used alpha here, so this should be alpha, and this should be beta. So it's the absolute value of alpha squared, and probability of getting 1 is the absolute value of beta squared. And the state after each of those measurements is equal to 0 or 1. We already know the answer. But I just want to show you this kind of measurement operator formalism, and just show you that it basically gives the same result. Okay. So in this case, the measurement operator is equal to 0. Sorry, the state that we're trying to measure is 0. So the measurement operator is this outer product of 0, 0. Then the easiest way to actually work this stuff out is you could do this kind of big matrix multiplication that I mentioned over here. But actually the easiest way is to note that this probability here, you can actually just write it like this. I just put brackets around here. And this is like m0 times by the state vector. And this thing is actually just equal to, so this thing here is actually just equal to the same thing on the right there. But then you just take the conjugate transpose of the whole thing. Okay. So that basically means once you've worked that out, you just take the conjugate transpose of that, and then you've got that. So it just saves you a little bit of work. Okay. So first, let's work out what this thing m0 times this here, the state psi is. So just basically just substitute stuff in. So m0 is that. Okay. This state here is this alpha 0 plus beta 1. Fine. And the way that you do this multiplication here is that you just, multiply each of these terms one by one. And what you basically do is you just, these ones here, when you multiply this and this, then, for example, you get this inner product of 0 and 0. Inner product of the same vector is always just equal to 1. Okay. And for this one, for the second term, the inner product of 0 and 1 is just equal to 0 because they're orthogonal vectors. Okay. So this second term is 0. This one was like 0, 0 vector times y inner product of 0 and 0, and that's equal to 1. So it's just equal to alpha times the 0 vector. Okay. Now, the probability, as I've said, so this thing here is this part of this equation. And then to get this part of it, you just take the complex conjugate transpose of this. And to take the complex conjugate transpose of this, you basically just, for any numbers here, you just take the complex conjugate. And there's no transpose because the number, there's no such thing as a transpose. You can't, it's not a matrix. So just take the complex conjugate. And this vector, you just turn it into the row vector, or the conjugate vector version, right? Okay, so that is this part of it. And then you just multiply this part, which is the first part, to the second part. And then so you get alpha star plus alpha, so that's mod alpha. And then again, you got this inner product of 0 and 0, but that's equal to 1. So it's just alpha squared. Okay, so that's exactly what we expected. The probability of this should be alpha mod squared. The measured state is just this m0 times by the state. So that's what we just worked out here. So it's the same calculation. It's alpha times the state 0. And then you divide by the square root of the probability. So we've already worked out the probability. So just put that guy in there. So it's going to be alpha times by the vector divided by the modulus of alpha, not squared because of this square root and the squared here, right? They cancel each other. So it's alpha divided by alpha mod, and actually that's equal to whatever the phase of this complex number alpha is. So remember, any complex number, you can always write it as r times e to the I theta. So if you go back to the lecture on complex numbers, then it's equal to r times e to the I theta, and then the modulus of a is actually just always equal to this r, right? So if you put like alpha is r e to the I theta here, and then modulus of a, so the r's cancel, and then you just get this phase here, whatever the phase of alpha is. So that's basically how it works, and so I'll talk about this phase here later. Actually, it turns out this doesn't really matter. You don't have to worry about it. So I'll tell you in a couple of slides, but basically what this says is that it totally agrees with whatever we were saying before. You get the probability of alpha squared, alpha mod squared, and the new state is just 0. But you get some phase here, okay, for this calculation. But actually, it doesn't matter. Okay, so that's how that works. For the one case, it's basically exactly the same. Again, the steps are the same. I've written it all out there, so maybe you can just go through and check that it all works. Basically, the only only difference here is that the projector is 1, 1, so that you pick out this beta factor, and then all the factors are beta, and the phase here is e to the I theta beta, where this is the phase of this complex number beta. Okay, so we can do it like that. And by the way, so you might be wondering, what's this bracket notation? So this stuff that I've been using, this notation where the vectors are in this angular thing, this is so-called bracket notation because essentially another way to call these states, so this thing here is called a ket, so something, where it's like the regular vector, it's called a ket, and this thing where it's the conjugate vector pointing the other way is called the bra, and together they form a kind of a bracket, right? Because brackets look like this. So that's why it's called bracket notation. I didn't make this up. It's just standard kind of quantum mechanic lingo. So this is just another way to call it. I think a guy called Dirac started to call it this, and then everybody else started to use it. I think he was famously a humorless kind of man. But, there are some amusing stories of people talking to Dirac and having awkward conversations with him. You can look that up. Okay, so that's one way to work this stuff out. Another way is to use the matrix notation. So I can just go through again this example. So if you go back to the lectures on the linear algebra, this outer product, so remember this thing is 0 outer product with 0, is actually this kind of matrix here, 1, 0, 0, 1. So we can actually do this whole thing with matrices as well. If you prefer the matrix way, then go for it. You can use that instead, basically totally equivalent. But sometimes this bracket notation actually saves you a little bit of kind of algebra. In the matrix notation, you find that you're doing all these matrix multiplications all the time, and they can be a little bit tedious, but in this bracket notation, it actually can look a little bit simpler. Of course, they all give the same answer. Okay, so how it works is that, okay, so we've got to work out this m0 times the state thing. So our state written in the vector notation, like in terms of the components like this is alpha and beta. So we just go and multiply this matrix with this vector. Okay, so again, we take this vector, whoops, okay, we take this vector and we multiply it by that row, so it's alpha times 1 plus beta times 0, so that's alpha. Over here it's alpha times 0 times plus beta times 0, so that's 0. Okay, so that's the vector that we get. The probability is again this thing where you take this vector and then multiply by the conjugate vector. So we take that vector, find the conjugate vector, so we put it on its side, take the complex conjugate, and so we multiply this out. So again, you take this column, multiply by this row, so it's alpha times alpha star, so that's alpha mod squared, plus 0, 0. So that's the probability. So, okay, good, it agrees with whatever we were trying to do. And the measured state is this m0 psi divided by the square root of probability. So it's just this vector divided by the square root of this probability. So the square root cancels this squared here. So it's alpha 0 divided by 1 over alpha mod. And again, you get e to the I alpha, theta alpha for whatever complex number you're dealing with, and times 1, 0. So you do get this 0 case. The 0 is defined as this element here. So you get the same answer. So you can use either way, and always gives the same result. So I won't go through this one case, but you can have a look at that yourself. Okay, so just to check that the measurement operator method also gives the same result for the second measurement. Let's just also go through that. I'll just go through it in the Dirac bracket notation. So suppose after the first measurement you got this 0, and say we're going to do our measurement again. So let's just check that the measurement operator formalism gives the expected result, that it basically just gives 0 again. Okay. So after the first measurement, I should have written e to the I theta a here. So here's our first measured result here, right? That's what you get over here. Now I'm going to apply this measurement operator 0 to this case, right? So here's our original state. That's the original state that we started off with. And then the, right, oh, sorry, I mean, okay. So the original state is really actually this part, this, and then this phase. Here's the measurement operator, m0, and so what you get is actually this inner product plus this state times this state. This inner product is just 1, and so you just get exactly the same state, even with that phase. Probability is going to be this state times by the conjugate vector version. So when you substitute this into here, and then take the conjugate version. So this conjugate vector here is actually going to be e to the minus I theta a, and then the conjugate vector 0. So when you multiply this part by this part, then actually this e to the I thetas, they all cancel, and you just get 0 out inner product 0, and that's 1. Right? So with probability 1, you get this outcome 0. So that agrees with whatever we said before. The measured state is, according to the formula, it's m0 of whatever you had divided by this square root of the probability. So this numerator is this, so e to the I theta 0 divided by square root of the probability. So square root of 1 is 1, and so you just get the same state. So you get exactly the same state as you put in. So actually, it's a bit different to what we wrote, only in that there's this phase that's like floating around here. I'll talk about in the next slide. For the case of the 1, so this is the case. So I didn't write it here, but of course potentially you might. Well, this measurement apparatus has two outputs, right? So you say, what is the probability of it getting 1? Well, I can just work that out using this. So let's first work out what m1 times this state here is, this input state. So it's just equal to, sorry, this should be alpha, not beta there. Okay. So this e to the I theta times by the measurement operator for 1 is 1, 1. So this is the measurement operator part. That's M1. Here's the state, that, which I've just pulled out the front. So our inner product of 1 and 0 is 0. So this whole thing is just 0. Okay. And the probability, this is 0. And then the conjugate vector of 0 is just 0. So 0 times 0 is 0. So the measured state is also 0. So everything here is basically just 0, and that's consistent with what we said here, because if we got 0 on the first time, then with 100% probability we also get 0 on the output here. Another way to say that is that there's 0% chance of getting the other outcome, and that's basically what this is saying here. Okay. All right, so yes, so now let's talk about this phase that's always been floating around here. So after the first example, we always had it that we had this phase, e to the I theta, and as I've sort of alluded to already, this phase actually never really matters. You can actually have any kind of phase multiplying a quantum state, and it never really affects the any kind of experimental outcome. Doesn't really affect anything. It's sort of like a free parameter there that's in the theory, and it basically doesn't really affect any of your outcomes. And you can kind of see this by, if we go back to like the previous slide. So here, notice that when we worked out this probability here, these phases, this e to the minus I theta and the e to the I theta here, they kind of canceled, and you just got 1, right? So these phases canceling is something that always basically happens if you measure this these kinds of outcomes, and so it's kind of unobservable in terms of what you are actually kind of measuring. So so these global phases. So whenever you have this kind of phase that's multiplying the wave function throughout, it never matters. Okay, this is, so be careful that this is different to saying that So say I have this state of, say, 1 over square root of 2 of 0, and then I have some phase, say here, multiplying on the 1, right? So this is a case where phase does matter, actually, and we'll talk about this more later. Having this phase actually is a different state. So different phases here do change it. So this matters. But if you have a different state, say e to the I phi over square root of 2, and then say 0 plus 1. So this is a case where it doesn't matter because it's multiplying through the whole wave function, and each of the terms all have this state. So this is an example of this global phase. This is actually an example of a relative phase between these, because this phase is only on the 1 and not on the 0, right? So this is not a global phase, and it's actually important to keep any phase here, whereas here it's actually not important at all. So so just to drive the point home, I guess. So all these states here are actually, physically speaking, exactly the same. So the state psi is completely physically equivalent to the state minus psi, or the state I times psi, or even the state 1 minus I square root of 2 times by the state. So all these states, there's physically no difference to the actual state. Okay, so whenever you get a global phase, it doesn't really matter. Everybody that knows quantum mechanics knows that it doesn't really affect anything. So what you often find people doing is to just kind of immediately drop the phase. And even here, I did it already because I'm so used to seeing the global phase and knowing that it doesn't matter, that I've kind of thrown it away, and I forgot to include it. But of course, technically, when you do this calculation, it's right there. Okay. All right. So let's just do a little bit of practice on this. So just to finish up this lecture. So for example, let's go back to this exact same example that I started off with. So I've got this electron and it's going either left or right. Started in this wave function, and let's use the measurement operator formalism to find this probability. So the way that you do it is, of course, so the probability getting 0 is equal to the psi of m0 m0 times psi, and m0. So the kind of easy way to work this out is to just work out what m0 psi is, and then later on we can just take the complex conjugate to do that. So we can do this, say, using the Dirac notation, bracket notation. So this is 0, 0, and then we multiply it by this root 3 I over 2. And because of this 0 and the inner product of 0, this is going to be 1, like the inner product of 0 and 0, and the inner product of 0 and 1 is going to be 0, so we don't have to worry about the second term, and so we're just going to get root 3 I over 2, 0. So that's our value of m0 times by the state psi, and then we can work out that the probability is just the conjugate vector of this. So it's going to be 0 multiplied by root 3 minus I over 2. times by this vector here, so root 3 I over 2. And these i's cancel, so we did already something very similar calculation. So this is going to give 3 over 4. And for finding the wave function after the measurement, then in this case, the new wave function after you measure 0 is just this m0 psi divided by the square root of this probability. So it's going to be root 3 I over 2 state divided by square root of this probability, 3 over 4. So this square root of 3 over 2 and the square root of 3 over 4, these are the same. So you're just going to get I times 0. And this I is actually physically kind of irrelevant. We don't really have to worry about that. Okay, so I think that basically concludes this lecture. So in the next lecture, we'll talk a little bit more about basis rotations. So okay, so that's it for this lecture, and see you next time.